Okay, let's get started. First of all, I want to clarify the relationship between our matrix extension and the vector extension. Our matrix extension proposal is highly inspired by the RISC-V vector extension. However, it is a standalone extension with no need of vector extension support. For implementations with both vector extension and matrix extension, we do provide another extension named ZMV to bridge the vector extension and the matrix extension. With ZMV extensions, vector registers can exchange matrix data with memory as well as matrix registers. So the vector extension and the matrix extension can work together smoothly. We will show the details later. So the main idea behind our matrix extension proposal is the tiled matrix multiplication algorithm. Suppose A is a m by k matrix, B is a k by n matrix, then the product C is a m by n matrix. The tiled matrix multiplication algorithm partitions the large-scale matrix A and B into small-scale submatrices, also named tiles, and iteratively compute tile matrix multiplication in 3 levels or loops. We use tile M, tile N, and tile K to describe the tile shapes. Yeah, tile M, tile K, and tile N. That is to see the matrix A tile. The tile A is all shaped tile M by tile K, and the tile B is a tile K by tile N submatrix, and the tile C is a tile M by tile N submatrix. Okay. So we think the tiled matrix multiplication is friendly to memory access, as we can load and store a tile row by row, which takes advantage of unistride performance. Also, the tiled matrix multiplication algorithm explores data reuse inside tiles. For example, an element inside this tile A is loaded once and involves in tile N multiplications here. So it reuses each element in tile N for tile N times. And also it explores tile reuse by especially when we compute 2 tile slices simultaneously. So we load tile A once, and it will use the twice with by multiply with 2 B tiles. Yeah. Okay. So in a nutshell, our matrix extension provides a portable and direct support for tiled matrix multiplication. Okay, let's get into the details of the proposal. The matrix extension adds 10 matrix registers and 5 unprivileged CSRs to the base scalar RISC-V ISA. Each matrix register can hold each register can hold an entire tile. Of the 10 matrix registers, 8 of them are tile registers, and the left 2 are named accumulator registers. The tile registers are for input matrices, and the accumulator register is for the product matrix. We use different registers for sources and products because the products can be widened. For example, int8 multiplication can generate int16 products. This is double widened, or it can generate int32 products. That's quad widened. There do exist methods to combine several normal registers to form a widened register, but we reckon that by dividing matrix registers into tile registers and accumulator registers, it's much simpler and more friendly to programmers. About the CSRs, we add 5 unprivileged CSRs. The tile M, tile N, and tile K, as the name shows, it describes the shape of each tile. and they hold 32 wide integers specifying the shapes for tiled matrix. These three registers are really only UCSRs and can only be updated by MSAT tile instructions. Besides, the M-type CSR provides the default type used to interpret the contents of the matrix register file. The M-type CSR has three fields: the MIL, M matrix illegal bit, MACCQ, which indicates the accumulated types, whether it supports up to quad width or double width only. And the third field is MSEW. The value in MSEW includes the selected element width. The M-type CSR is also read-only and can only be updated by MSAT type instructions. So each heart supporting a matrix extension defines three parameters to constrain the shape of tile registers. ELEN here indicates the maximum size in base of a matrix element that any operation can produce or consume, which must be a power of 2. The definition of ELEN is similar to the definition in vector extension. The MLEN parameter indicates the number of bits in a single matrix tile register. It must be a power of 2 and must be no greater than 2 to the 32nd power. The RLEN parameter indicates the number of bits in a row or a single matrix tile register. It must be a power of 2 and must be no greater than 2 to the 16th power. We have the constraints here. The ELEN must be less than RLEN and the RLEN must be less than MLEN. So a tile register can hold a matrix tile as small as 2 by 2 and as large as 2 to the 15th power by 2 to the 16th power. Okay, here is the layout of a tiled register and the accumulator registers. For a tile register, the MLEN indicates the total bits here, total bits, and RLEN indicates the number of bits in each row. For an accumulator register, we support double bits. So the total bits of accumulator is twice the MLEN. And for an accumulator register with quad width, the number of bits in a single accumulator is MLEN times 4, and the bits in each row is also RLEN times 4. So let's take a look at the instruction format. The instructions in the matrix extension use a new matrix code 1110111, and the opcode is here in the opcode map. The above one is for the vector extension. Okay, instructions are divided into configuration instructions, arithmetic instructions, data move instructions, and load store instructions. They are differentiated by base 14 to 12, the func3 field. So the func3 field 111 includes configuration instructions, 110 includes arithmetic instructions, 101 includes data move instructions. They are specially used in the following VMV extension. 002.011 includes load and store instructions, and also the value represents the element width or load store. So the configuration instructions include two kinds of instructions, the MSAT type and MSAT tile. The MSAT type instructions set the M-type CSR based on their arguments encoded in immediate or general purpose register RS1. Yeah, the immediate or the register RS1, and write the new value or M-type into the general purpose register RD here. Here are some examples. So the style is quite similar to the vector extension. We take one example, the M-site type T0E8ACCQ. This instruction will set the SEW base in M type to 0, which means it's 8 base. And it will set the MACCQ base to 1, which means the accumulator register supports quad-wise. The M-site tile instructions set the tile M, tile K, and tile NC stars based on their arguments and encoded in immediate or the general purpose register RS1, and write the new value into general purpose register RD. This quite similar to the vset VO instruction in vector extensions. So there are 3 values called TM max, which means the maximum tile M, and TK max and TN max represent the maximum shapes of matrix tiles that could be stored in matrix registers. The tile M max is given by mlen divides rlen, which means how many rows you can store in a tile register. And the TN max is given by rlen divides SEW, which means how many columns you can store in a tile register. So the TK max is the -1 of TM max and TN max. Let's look at an example. If suppose mlen equals 256 and rlen equals 64, so the TM max is given by mlen divides rlen, so it's 4. And the TN max is related to the SEW settings. The SEW is 8 base. The T max equals to 8, and the TK max is the minus of the 2 is 4. And the SEW is 32 base, the T max is only 2. So the TK max is the minus of the 1 is 2. The M-site tile instructions set the tile M or tile K or tile N values obeying the following constraints. This is also similar to vset VL instructions in vector extension. Take a tile M, for example. If the application tile M is less than the TM max, then tile M is set to ATM. Then the tile application tile M is less than 2 times or TM max, then the tile M is allowed to be anywhere between half or ATM and 2 TM max. And when ATM is greater than 2 times or TM max, then the tile M is set to TM max. So this is quite similar to the vset VL instructions. Okay, let's look at this example. In this example, the mlen is 256 and rlen is 64. So the TM max is 4 and TN max is 8 under 8 base SEW. In the last iteration of the tiled matrix multiplication, the last one, the tile M is set to the matrix A is a 7x8 matrix. So the last iteration, the left tile is O shape 3x4. So the tile M is set to 3 and the tile K is set to 4. Okay, let's look at the load instructions. The load instructions load a matrix tile from memory to a matrix register. The first letter here, M, indicates is short for matrix, which indicates is a matrix instruction. And the second letter L here indicates stands for a load operation. The third letter here may be A or C or B or C. So these letters indicate the shape of the tile to be loaded. Also, it indicates the destination register types. So if letter is A, it means load a left matrix tile to a tile register. The shape of the tile is tile M by tile K, and the destination register is a tile register. But when the letter is C, it means we are about to load a matrix tile M by tile N to an accumulator register. And the EEW here stands for effective element width, and it encodes the element width in load store instructions. The M after the dot stands for the destination register types. So here is a matrix register, and the MD here represents the destination matrix register in the matrix destination register, and the general purpose register RS1 gives the base memory address of the tile, and the value in general purpose register RS2 gives the row size in bytes. That means the gap between two consecutive rows. So here, for the complete instruction here, MLAE, it loads tile A from the left matrix to a tile register, and the MLCE here, it loads tile M by tile N tile to an accumulator register. The load instructions also support transposition operations by adding another letter T here. It means we are about to load a transpose tile to a matrix register. So the MLAT here, it will the tile shape is given by tile K by tile M. For a normal MLAE instruction, the size, the shape is tau M by tau K. So this is a big difference for load transpose tiles here. The shape is transposed. And the store instructions are quite similar to the load instructions, except they have opposite directions. Yeah, they transfer data from matrix registers to the memory. And the store instructions also support transposition operations. And the arithmetic instructions are divided into two kinds of arithmetic instructions. One is the matrix multiplication instruction, and it's the highlight of matrix extension. So we support integer matrix multiplication as well as floating point matrix multiplications. So there are totally 5 instructions support double widened and quite widened. So the MMA here, this instruction will produce a single width results. And the MWMA instruction here, it will generate a double widened result. And the MQMA instruction will generate a quad widened result. And at the FMA and FWA represents floating point matrix multiplications. The other kind of arithmetic instructions is element-wise instructions, including matrix matrix additions, matrix subtractions, and element-wise multiplications. We also provide type convert instructions to convert from different data types, from integer to float, or floating point into integers, or we can use type convert instructions to narrowing to narrow a floating point or widen a floating point, which means we can convert a FP32 floating point to FP16, or we can also convert FP16 to floating point 32. Okay, here is a matrix assembly code example showing the process of the tiled matrix multiplication algorithm. The most important three instructions here inside the inner loops they're here. The first one, MLAE 16-M. This instruction will load a tile from the left matrix to a tile register, and this instruction will load a tile B from the right matrix to a tile register, and this instruction is the matrix multiplication instruction, which conduct tiled matrix multiplication and put the results in an accumulator register. So after the iterations in the K loop, we get the final results or the accumulated tile, and we can the next we will convert the floating point floating point 32 results to maybe to floating point 16. And store the results back to memory with matrix store instructions. And here the three loops here. In each loop we will set the respective tile CSRs. As mentioned before, we also provide several other extensions. The first one is the ZMV extension, and it is used to bridge the vector extension and the matrix extension. With ZMV extension, we can exchange data between vector registers and matrix registers. Also, we can exchange data between vector registers to and from memory. Also, our extension also provides element-wise multiplying with a matrix register and a vector register by broadcasting a vector register to a matrix tile. So here is gives a view of the ZMV extension. So here is the tile, the layout in memory. With the ZMV instructions, we added these two data passes. So this pass will exchange data between matrix type data between a memory and the vector register, and with this data pass we can exchange data between matrix register and the vector registers. Yeah. So first, also the load instructions. This is quite similar to the matrix load instruction, except the destination here is the letter here after the dot is V instead of M. It means the destination register is a vector register. So the RS1 also is the memory-based address. RS2 is the row stride in bytes, and the A, B, C here also indicates the shapes, the shapes of the tiles. So take this instruction for example, the MLAE .VD instruction. It loads a tile A from the left matrix to a vector register VD. Yeah, the store instructions are quite similar to the load instructions, except they have opposite directions. And the data move instructions moves data between matrix registers and vector registers. The matrix register supports two directions, the row direction and the the column direction. It is indicated by the letter in the instructions R or C here. So the R here represents the row direction, and the C here represents the column direction. And the letter here A, B, and C also indicates the shapes of the tile. Okay, we'll take example. So the first instruction MMVAR, which means .v.m. This instruction those Elma slices from the matrix register MS1 to MS1 here to the vector register. Totally Elma slices started in RS2. The RS2 here indicates the start position, the start position of the slice. And also the matrix extension provides matrix element-wise multiply by matrix multiplies with vector. So the vector, it also supports two directions, which means the vector register will broadcast to a whole matrix along the row direction or along the column direction. So the first example, the example above here, so this broadcasts the vector register to a matrix along the row direction, and the example below broadcast the vector register to a matrix along the column direction. And then the two matrix tiles compute element-wise multiplications and get the results and put results to the MD. So here is another example which fused matrix extension and vector extension. So the above part is the same as the previous example, which shows the process of the tiled matrix multiplication. And after the results are gathered, we move the data to the vector registers with data move instructions and use the vector instructions VFMX to conduct like a ReLU activation function in like AI inference workloads. So this is example shows how matrix extension work together with a vector extension. Besides, we also the default matrix extension supports only standard IEEE floating point data formats. We also explore two other extensions to support various floating point data types, including TensorFloat 32 and also bfloat 16. The instructions are quite same, except we add a single bit for the TensorFloat 32 and the bfloat 16. We add one respective bit in the M type CSR for each of the extension. For the BF16 format, data are stored and computed in the BF16 format, and the results can also can be BF16 if it's the single width, if it's a normal width, and if it's it can be FP32 if it's double widened. And the TensorFloat 32 data format is only used in computations, and they are developed to achieve better performance on matrix multiplications and convolutions. So by running input floating 32 data to have 10 bits of mantissa and accumulating results with FP32 precision, it maintains FP32 dynamic range. The data are stored in registers in FP32 formats and are only computed in TensorFlow 32. Yeah, we add another a bit, the bit 5 in M-type CSR to enable TensorFlow 32 extension. Okay, based on our previous works, we have open sourced a lot of our works. The first is the matrix specification, and we also developed related toolchains like LLVM. To support matrix extension, to support our matrix extension proposal, and we developed a RISC-V instruction set simulator Spike based on Spike to support matrix extension to support the matrix extension, and also we enhanced the boom generators in ChipYard to support the standard RISC-V vector extension 1.0 and also our matrix extension, and also we the RISC-V PVP matrix here is a verification platform. We implement the platform to support regression verifications on vector extensions and matrix extensions. And the RISC-V DNN here, it is a small deep neural network library for RISC-V. There are many implementations, including DNN operators, or the whole ResNet inference is implemented using RISC-V vector extension and matrix extensions. So our future works will include we want to add another extension, the image to column matrix extension, to perform the image to column operation on the fly by adding a new load instructions. And also we will further optimize our ChipYard implementations and provide the performance data for reference. Okay, that's all for the talk today. Any questions?
Yeah, anyone, please?
Hello, I have some questions about your proposal. My name is Qiu Jing. I come from T-Head Alibaba. We are very interested in your proposal, and we work on it for some days. And I have perhaps four questions about your proposal. I also print out it on the chat box. The first is the number of source register is set to 8, and you set the accumulation register to 2. Why you choose this 2 number? Why is 8 and 2?
So based on our simulation results, we found 8 registers, 8 tile registers are enough to get ideal performance. Okay, but we want to leave it open to further discussion.
Okay. Then the second question, is there any constraint relationship between RLAN and VLAN? How to set VRLAN without CSR? I think there is no CSR to set RLAN.
RLAN, okay. Yeah.
That's the row length. I think that's an implementation issue, right? That's implementation defined. It's not configurable.
So the programmer can read it from CSR, or they just don't know?
It's a read-only CSR, so it can be read.
Is it something similar like when you set the vector length to the maximum and then the instruction tells you what's the maximum that they can support, and it's told to the software. Is there any mechanism like that?
Sorry, I beg your pardon?
Yeah. So for example, on the vector extension, you can instead of assuming what's the vector length supported by the hardware, you can set a very big vector length, and then the hardware will tell you what was the maximum that it could actually support. So when you do the vset, the set v type, so the instruction itself will tell you what was the maximum that it could grant, and then the software can use this for traversing the vector or the matrix. So this RLEN is something, I guess it's something you can also get returned from hardware to software when you set the matrix shape, right? It's informed from hardware to software. Right?
Yes, you're right. Yes,
Yeah,
you're
the
right.
MSET instructions. Yeah, can you just show the MSET instructions? I think it will answer there, where you set the max value following.
So the RLEN and MLEN parameters, they are they are hardware implementation parameters defined by the hardware implementers. Yeah, we should support reading the RLEN to better help the programmers. Yeah, we will add it later.
Okay, thank you. And the third question is that we noticed that the registers for different purposes have different size. For example, matrix A, matrix B, or accumulation at matrix. So how to save these whole register files when context switched? I think it's difficult to use load store instruction to save all these registers.
Yes, that's a good question. Currently, we did not consider the environments when or the context switch. We think, the tile registers, they hold too many levels, and we think the cost to load to restore, to save and restore is too large, and so in our current circumstances, we think we did not include the context switch in this chapter.
Yeah, the vector spec has the exact same problem, and basically the model is save and restore everything if you want to do a context switch. And so there's whole register load and whole register save instructions in the vector spec to do this. I'd imagine if you look at the tile, the matrix thing, you'd need something similar.
Sorry to weigh in. So there is a way of dealing with context switching in Intel's AMX. So basically, instead of so you have instead of having a load instruction, you have an instruction for telling where the data should be loaded from. And every time that there is a context switch, when you come back, there are these config registers from where the hardware knows where to fetch data. So it's like, you set up the address for loading the data whenever you have to context switch. I think that's how it works on AMX. So rather than loading the stuff, you set up configuration for the thing to be loaded on demand. I think it's something along those lines. Typically when you have this kind of big registers, and there is context switching, what you have to do is try to make them work as a cache. So if there is context switch, the cache is cleared, and you lose the content. And next time you execute, you may have to populate the cache before you continue executing. but you are free to stop and restart at any time. So that's the kind of pattern that we will have to look at if supporting context switching, I guess.
But it's even worse than that in the vector spec. It's not just a context switch. It's on a function call. You can't rely upon having access to vector register, any vector register after a function call. So there's no ABI for passing values by vector register.
Oh, I see the point. Okay.
I think vector provide a dirty bit to support us to quickly just the context switch, only load store the dirty vectors registers in this progress. But if you do the matrix like this, we should store and load too much, perhaps. Okay, we have the first question is that will the toolchain provide C interest for your matrix extension? Since we didn't find ACC or GCC for a compiler for this project.
I have a question. If that's okay, can I ask a question?
Please go ahead.
Okay, sure. I'm afraid I didn't know this presentation was going on, and I actually sent an email out to the email chain that had been talking about this while this talk was going on, and then I found the talk, so I joined in. I missed the first 15 minutes. I apologize. My question by email, I'll repeat it here just for simplicity. It was about how did you consider the vector spec tie-in with this? And I see from the presentation that you considered it quite closely, but it's a loose tie-in. And by a loose tie-in, what I mean is you're assuming completely different storage. You have matrix tile registers and accumulator registers that are completely separate from the vector register state. And I'm wondering if you thought of integrating those and what the challenges that might be.
Hard question. May I ask you through email later?
Yeah, you can reply to the email chain if you want. I just thought it might be easier. It's just about the vector state and the tile state. They're separate. Can you combine them and have a single register file?
You mean use the same register file for vector and matrix?
Yes.
Okay. We have tried to use this solution, but from our practice, we think it's really if you want to implement a matrix multiplication with large compute performance, this will require a very large vector register, so the VR max can be very large. And another thing is the memory access patterns. We did not find a way to overcome to load strided instruction to registers. So we use a separate tile register, so we can we think it's more friendly to memory access.
But Leo, one question. I have the impression that well, you published a paper last year, I think, describing some proposals for matrix multiply, and well, in this paper, you were actually reusing the vector registers and just adding some extra configuration for defining the shape of what it was stored in there. So my impression is that you tried this approach of using exactly the same register file and then you switch to this other approach of having to register files. Am I correct that you tried both and you like more what you presented us today?
Yes, we published a paper last year. The paper is based on our last two generations or ASIC types, or ASICs, and the proposal today is different with the paper last year. The main difference is we used registers instead of buffers to implement matrix multiplication. The way the matrix multiplication conducts is quite similar, but the storage types, is the biggest difference. Yeah, they use registers instead of buffer. We think it's more friendly to the tool chains, to all compilers, to get to make it more with better programmability.
And you also mentioned that you want to decouple the size of the matrix and the vector length, right? Because you want to support very big matrices, and you don't want to force very long vectors because of that, right? Am I correct?
Sorry, I didn't get the point.
By having two different register files, one for the matrices and another for the regular vector functionality, by having them separate, basically you allow the size of the matrices to grow wild, while the vectors can stay short, and maybe you don't want to force increasing the length of the vectors for vector extension, just because you want a bigger matrix. So you want to have them like separate, so you can make one of them grow a lot, like the matrix grow a lot, without forcing the vectors to grow longer, right? Is that possibly one of the reasons for keeping them separate?
I'm sorry, I really can't catch up with you.
It's okay. So I'm sure that there are advantages on having to separate register files, and I think for me the big thing is that you've tried both approaches and you like to have them separate. So that for me is important. Thanks for answering the question. I think you already answered this question. Any more questions?
Can you leave your questions in through email, and we'll give you detailed explanation later. I'm really I can't catch that. Sorry.
It's fine. Thanks for your time, and if anyone has any more questions, just follow up later by email or something. Many thanks, Liu, for your time, and I know it's very late in China at the moment, and you are still here presenting in the middle of the night. Okay, I think does anyone have any more topics for today?
Thank you very much. Are your slides available anywhere?
Sorry?
The slides.
Can you share your slides?
Sure.
Great. Thank you very much. Very, very interesting work. Really like it.
Thanks.
Okay, so yeah, send us the slides so everyone can have them, and we can follow the links to GitHub and look at all the stuff. Thank you for everything.
Yeah, good luck.
Thanks. Thank you for your time.
Okay, so yeah, we close the session, and yeah, so also, so guys, send me topics for next session, and yeah, basically we are running out of subjects, and yeah, if you have stuff that you've made some progress with or whatever, yeah, send me an email, and we can define an agenda for next meeting. Okay, because otherwise I have to start canceling meetings, and yeah, if there is not enough stuff to talk about, yeah, it doesn't make sense to call people for a meeting. So please send me topics. Okay, thank you. Thanks everyone.